This lesson is over 4.7, L'Hopital's rule and indeterminate forms. This is the last lesson of Unit 4 and the most important theorem of the unit. So thinking back to limits, always try to plug it in first to see the limit. If it equals a value, then you are pretty much done, but in calculus it's never that easy. Sometimes when you do direct substitution, you get an indeterminate form, and indeterminate forms are anything that's 0 over 0 or infinity over infinity. Indeterminate forms means that the limit cannot be determined without an additional support or analysis, hence the name indeterminate form. There are other indeterminate forms besides these two. There's these ones here, but they won't appear in AP Calculus, so you don't have to worry about those. But going back to that problem, so if we plug in 4 over 4, we do get 0 over 0. I'm sorry, if we substitute 4 into each x, you do get 0 over 0, which is an indeterminate form. Normally, we would just factor, like we did here and here. When you factor, you get the x minus 4's cancel. And that, again, that's what made it 0 over 0, because if I plug in 4, I'm going to get 0 over 0 times anything is 0. But once we cancel those terms out, we're left with these two, and then we can do our direct substitution. Okay, so what happens if we cannot manipulate it by factoring or some other process? And we're going to consider this function. So again, if we substitute 0 here in the numerator, we're going to get e to the 2 times 0, which is 1, plus 0 minus 1. And so that all equals 0. And then if you substitute 0 into the denominator, you're going to get 0 squared plus 4 times 0, which is also 0. So we do have indeterminate form, but this cannot factor. So what else do we do? And that's where this new rule called L'Hopital's rule comes into play. So I'm going to show you what it is, and then I'm going to try to explain why it works. There's also better videos on the internet if you want to go check those out, but I'll try to give you like a rundown of why we can do this. So basically, L'Hopital's rule says if the functions are differentiable on an open interval, a to b, and that contains a value we called c, and it doesn't have to be differentiable at c, and we have to assume that the denominator is not 0, the derivative of the denominator is 0, then basically, if the limit of the numerator is 0 and the limit of the denominator is 0, then we can just take the derivative of the top and the bottom and then plug in the limit after that. That's what L'Hopital's rule is. And again, this can be infinity too. So if it's infinity over infinity, that was awful. An infinity over an infinity, you can take the derivative of the top and take the derivative of the bottom and then just plug in the value you're looking for and see if it works out. If it doesn't work, you can repeat this as many times as you need. And here's a way that I'm going to try to explain it. So let's say that we have a curve. Let's say it's not a polynomial, like something like that. So basically, when you're taking a derivative at that point C, you're basically finding the equation of the tangent line. And the tangent line and the curve are basically the same thing when you get infinitely close to C. So as you zoom in this way to point C on the curve versus this way on the tangent line, then the values are basically the same. And remember, the derivative is the slope. Right? So basically, instead of using this complicated equation, you can just use its derivative slope and try to find the value that way. And that's kind of loosely why it works. I don't know if that was a good explanation, but whatever. So a couple important things about L'Hopital's rule. It is a theorem. You always have to check conditions. When you check your conditions, they must be in an indeterminate form. So like this or like this. And please do not write equals 0 over 0 because these are indeterminate forms, not numbers, so they're not equal to it. Right? That's just a little nuance. Don't write equal to. So when you're doing this, when you're showing your work, write the limit of the numerator and the limit of the denominator separately. Show that they're both infinity or both 0. And again, both have to be infinity or both 0. Then you can apply L'Hopital's rule. If one of them is 0 and one of them is infinity, then you actually have your answer already, right? If the numerator was 0 and the denominator was infinity, the limit is 0 because you have 0 divided by a big number, which is 0. And if it was flipped, if the limit of the numerator was infinity and the limit of the denominator was 0, then it does not exist because you cannot divide by 0. So again, both of them have to be 0 or both of them have to be infinity. And then apply L'Hopital's theorem. I'm just going to write it L prime H like that, L'Hopital's. Find the limit of the numerator and denominator separately. And once you have done that, write your answer as a ratio. So here, I have all of these kind of pre-done, at least the work. So again, this is how you would show it. So we have to check first our conditions. So let's plug in 4 to the top. 4 squared is 16 plus 8, which is 24. Minus 24 is 0. And then the denominator, we got 16 minus 16, which is 0. So L'Hopital's rule applies. Again, because that's indeterminate form. And again, that just means indeterminate. Now, we can take the derivative of the top and bottom. So if I take the derivative of the top, I get 2x plus 2. And then minus 0, but we won't write that. On the denominator, taking the derivative of the denominator, we have 2x. And then minus 16, the derivative of that is 0. So we have this part, and now we can substitute 4 into our equation. So 2 times 4 plus 2 is 10, divided by 2 times 2, 4. And so our limit is now 5/2. Oops, I goofed up. We have to substitute 4 in there, not 2. So the answer is 10 over 8, which simplifies to 5/4. Moving on to example 2. So again, we have to plug in 0. So e to the 0 is 1 plus 0 minus 1. So that equals 0. And then 0 squared plus 4 times 0 is 0. So again, we have indeterminate form. So now we could take the derivative of the numerator and the denominator separately. So the derivative of e to the 2x is going to be e to the 2x times 2 for the chain rule. The derivative of x is 1. And the derivative of 1 is 0. Now on the bottom, the derivative of x squared is 2x. And the derivative of 4x is 4. And now we can plug in 0. So e to the 2 times 0 is 1 times 2. And then plus 1. So that's going to give me 3 on top. And then on the bottom, it's just 4. And there is my limit. So we'll move on to example 3 and 4. Basically, we're going to use this table and this graph to find the limits and the derivatives, or to find the limits, technically. It does say that they're twice differentiable, which is part of the requirement of the theorem. Okay, so let's check example 3. We're going to substitute negative 2 into the numerator. So if we go to f of negative 2, that is equal to 1. So this is going to be 1 minus 1, which is 0. And then the bottom's a little easier. We have negative 2 times 2, which is negative 4, plus 4 is 0. So we have indeterminate form. Now let's take the derivative of the top. So the derivative of f of x is f prime of x. The derivative of minus 1 is 0. And on the denominator, the derivative of 2x is 2. And then the derivative of 4 is 0. So now we just need to substitute our value in. So we have f prime of negative 2 over 2. So the derivative at negative 2, so the slope of this line is going to be negative 1/2. And so my final answer is going to be negative 1/4. Example 4. So let's substitute 4 into our equation. G of 4 is negative 3. And then we're going to get 2 times 4, which is 8, minus 8, which is 0. So this is going to be negative 3 plus 3, which is 0. So the top is 0. And then if I plug in 4 here, I get 0. So again, we have indeterminate form of 0 over 0. So now we can apply L'Hopital's rule and take the derivative of the numerator and denominator. So if I take the derivative of the top, the derivative of g of x is just going to be g prime of x. The 3 is a constant, so it stays. And then we're taking the derivative of e to the power of 2x minus 8, which just stays the same, times the chain rule. And the derivative of 2x minus 8 is just going to be 2. The derivative of the bottom, the derivative of 4 is 0, and the derivative of minus x is just going to be minus 1. And so now, let's substitute 4 into our equation. So the derivative of g prime of 4 is going to be negative 1. And then 2 times 4, 8, minus 8 is 0. So this is e to the 0, which is just 1, over negative 1. So on the top, we're going to get 5. We're going to get 5, and then divided by negative 1. So we get negative 5. All right, example 5. So again, let's plug in 0 into the numerator and denominator. So the derivative at 0 is going to be 6. And cosine of 0 is 1. So this is going to equal 0. Now let's plug in 0 to the denominator. So g of 0 is going to be 0. And then the value at 0 is also 0. So again, we have indeterminate form. So let's take the derivative of the top. The derivative of g prime is g double prime minus the derivative of cosine is negative sine, and that negative will meet with that negative to turn it to positive. And then also we have a chain rule. The derivative of 4x is 4. Taking the derivative of the bottom, so we're gonna, this is another chain rule, so we're gonna have f prime of g of x, and then times g prime of x because of the chain rule. So let's substitute 0, and this is positive because it's a negative and a negative. And also we have 6 times 4, which is 24. Substitute 0 into the denominator. G double prime of 0 is, it's going to be 2. And then sine of 0 is going to be 0. So on the top, we're just going to be left with 2. Now, denominator, g of 0 is going to be 0. And let's find the derivative of f at 0. And the derivative here means the slope of the tangent line. So this is going to be negative 1/2. And oops, I goofed up again. I forgot to plug in the chain rule, g prime of 0. So g prime of 0 is going to be 6. So there's going to be a 6 here and a 6 here. So this is going to be 2 over, and then on the bottom, 1/2 times 6 is 3. Last question. So let's plug in negative 2. So g of negative 2 plus negative 2 squared. So I'm assuming g of negative 2 is negative 4. So we have negative 4 plus 4, so that is equal to 0. On the denominator, we have negative 2 squared plus 4 times negative 2 plus 4. So that's going to equal 0 once you simplify again. So we do have indeterminate form of 0 over 0. So we can take the derivative of the top and bottom. So the derivative of the top is going to be g prime of x. And then the derivative of x squared is going to be 2x. On the denominator, we're going to have 2x plus 4. So now let's substitute negative 2. Looking at g of negative 2, that gives me negative 4. So we have negative 4 minus 4 all over negative 4 plus 4. So we're going to get negative 8 over 0, which is not right. The top should be 0 as well. What did I do wrong? G prime of this is supposed to be positive 4. So again, we have 0 over 0, which is indeterminate form. That is awful handwriting. But again, what we're going to do is just take the derivative again. So the derivative of the top is going to be, and when I say the top, I mean of this function. So we're going to take the derivative of g prime of x and get g double prime of x. And then we're going to take the derivative of 2x, and it's going to be 2. On the bottom, the derivative of 2x, which is 2, and the derivative of 4, which is 0. So let's try again, and let's plug in negative 2. So this is double prime of negative 2 plus 2 over 2. And I think this will be right. So double prime of negative 2 is 3. So this is going to be 3 plus 2, which is 5 over 2. So that was the one case where we had to take L'Hopital's rule twice.